Right, so welcome back everyone. In our previous video, we finished the worksheet. Um, One thing that I forgot to mention then was that uh, even though all of us were maybe uh, picking things in different orders in that worksheet, we should have all gotten a topological order by arranging vertices by decreasing order of finish time. Okay. Um, it might be a different order. So your topological order might have been different from mine. You might have had a different way to take the courses in the computer science major than I did, but you should have also had a legal way to do it. Okay, so the last thing I need to do to close this out is to talk about the theorem, right? The theorem that we have built all of this on, and again, you want your slides handy, right? Is the theorem that claims that if we arrange things in decreasing order by finish time, that we in fact have a topological sort. And so this slide here outlines the proof, okay? And so the cases I'm outlining here, there are really three cases, is what the proof outlines. Okay? So here's the scenario. We have a directed edge going from vertex u to vertex v, right? And so imagine that you are accessing this edge, or you're trying to traverse this edge during depth first search. So hopefully you agree that there are three cases for vertex v. Either it's undiscovered, meaning it's white, or it's been discovered, which means that it's gray, right? Or it's been fully processed, in which case it is black. Right? So we're going to examine each of these cases one at a time as part of the proof of this theorem. So imagine what happens here. Right? So we're at vertex u, we traverse this edge to vertex v and find that it is undiscovered. Well, what do you think is going to happen now? We're now going to call DFS visit on v, right? And it's going to go off and do its thing, and at some point it finishes with vertex v, and only then does it go back to u and complete the processing of u. So do you agree that v gets finished before u? Right? So therefore it must be the case that the finish timestamp of v is less than the finish timestamp of u, right? Because v gets finished before u. So if I were to, so remember we're arranging things in decreasing order of finish timestamp. So u would come before v, which is exactly what we want, right? If this arrow indicates that task u must be performed before v, then indeed the fact that u has a greater finish timestamp means that it will get listed earlier than v in the topological order. Okay, so that's case one. Case two is actually a bit of a red herring. So what's happening here is we're saying that, okay, you're at vertex u and you encounter this edge and it takes you to vertex v, and v happens to be gray. Well, if you think back, this only happens if this edge is a back edge. Okay? But we're not allowed to have back edges because this is a directed acyclic graph. We don't have cycles, so there better not be any back edges. And so this case should actually never occur. Okay, so this is a bit of a red herring. This does not actually occur in a directed acyclic graph. Okay? And that leaves us with the third case, where at the point that the algorithm, the DFS algorithm, is traversing this edge, and it encounters v, and it finds that v has already been colored black, which means that we're already done with v. It's already been finished, right? And whereas u has not yet been finished with. So again, it must be the case here that the finish timestamp of v is less than, draw that better here, is less than the finish timestamp of u, and the same reasoning applies as we had in case one. Okay, so that's that's the proof. That's the reason this approach to topological sorting works just fine.